In the last lecture, what we did was to show that pronouns are in fact quotient groups. Okay, so last time, so they, something like they, then quotient group, QG. So this is what we did last time, and this lecture is an extension of that. And so this time, instead of just quotient groups, we're going to be talking about quotient spaces. So we're moving on from group theory into topology and algebraic topology. So if you guys don't know yet, topology is the study of shapes or geometric shapes, whether geometric or not, under the lens of stretching and squeezing. So topology is also called rubber sheet geometry because every shape that we consider or study in topology is imagined to be made out of a rubber-like material that we can stretch, we can squeeze, we can bend in any ways, but the only thing we cannot do to a single to that shape is tear it or take away a subset from it. So that's topology. So there's a notion of what is called a topological space. So that's from last time. This is what we're doing today. So this time, let's use a different pronoun. Let's say he, him is a quotient space. So in topology, we consider these things called topological spaces, which are basically sets that are equipped with another type of set that defines openness. So there's this thing called an open interval in mathematics, and it's basically a range of values, real number values. It's a range of real number values between two bounds. So an interval. So let's make a definition. An interval is a range of values between two elements of a set. And the thing is, we cannot define an open interval, which is basically an interval that does not include the bounds. I know it's a bit counterintuitive or oxymoronic to say that the interval exists without saying the bounds are part, but that's just basically saying all possible values between those two bounds, but of course not including those bounds. So that's what we mean by an open interval. A closed interval includes the bounds. But in the first place, when it comes to mathematics, instead of asking what we can do with it, we ask why. Why is it open? How do we even define openness? So that's where topology stands into. That's when topology comes into play. We define this thing called a topology over a set, which defines openness of intervals, and that's where we can define an open ball, which is basically just a set of points with a fixed distance. So basically all points within a circle, that's a ball. An open ball is basically a circle, or all points inside a circle without the boundary or without the circle itself. So all those points inside, but the outer part is not part. I know it's a bit counterintuitive, but that's the definition of a ball. So we define those balls, and then using those balls, we define openness. Okay, so this is the most primitive notion of openness and stuff like that. And because of that, we can demonstrate facts about continuity in calculus. So continuity is like I draw something without lifting the marker. So this is discontinuous, this is continuous. This here is continuous, this one with the line break is discontinuous. So topology allows us to do that. And okay, so a topology is basically all possible open sets. We define every element inside the topology of a set to be an open set. Every possible subset of the set. So there are certain rules that we follow when it comes to topology. These are the topology axioms, I believe. There's no solid name for it, but the focus is a topological space. So a topological space is any space you can think of that has a topology on it. So practically any set you can think of can have a topology, but there are some exceptions. Even the empty set has a topology when it is called the trivial topology. And so yeah, again, it is a sort of, I could say, parametrization or formalization of taking subsets or open subsets from the set and defining balls inside the set to define or rigorously define openness and continuity. Okay, so there are many ways of constructing spaces from spaces that we've already defined. So we have a regular topological space, and so the question now is, what the heck do we do with it? How do we construct new spaces from it? So there are many ways of constructing new space from it. There is a fibration, there is a product space, there is a subset space, subspace topology, or a product. So we can take a product between a space and itself to get multiple pairs or tuples of ordered sets. Of elements, distinct elements from that same set. So if I have a line, which we say to be a topological space, let's say a subset of R, and then I take its Cartesian product with itself. That means I take one element here and pair it with another element here, and then I put them into one single thing, which I define to be a point AB. And that AB is a part of a higher dimensional space, which is basically just us rotating this and turning it into a square. So this entire thing, if I call this interval I, this entire square is I cross I, and that is under the product topology. So every possible operation or construction we can do over a space, a topological space, carries with it a different topology that we do. Like say, if I take a subset of I, if I take this small part of I, this sliver of I, and then I tell you guys it is a subspace, it carries with it a topology, a new topology called the subspace topology. And these topologies are defined in many different ways. But what I want to focus today is the quotient space. So instead of thinking of he over here as a group, we're going to think of it as a topological space, and him is a subspace, which carries with it the subspace topology, or at least implies the subspace topology. And then from there, we're going to talk about the quotient space. But namely, what I want to say, the main idea of this lecture is that if he is a topological space, and him is its boundary, or actually he is a manifold, and him is a boundary, then he quotient him gives us a junction space of all possible points in him, or rather it gives us a quotient space. So basically, if he is an open, like a flat surface with a boundary on it, the quotient he him is basically us folding that into a higher dimensional space and constructing a three-dimensional space out of that two-dimensional shape. Now, topologically speaking, that is just that's from one space onto two space. Okay, 2 dimensions, 1 dimension to 2 dimensions, topologically speaking. Because topological dimensions is different from geometric dimensions, in which way the first dimension is just curves. They are curves, any possible thing you can think of. Something like this, hell, even like this. Those are curves, okay? One-dimensional objects. A two-dimensional space is already a surface. Three-dimensional Three-dimensional space is a hypersurface. If I remember to calm down. Okay. So we will mainly be focusing on two-dimensional shapes, as in like geometrically speaking. So flat volumes and stuff like that, like a disk, or things homeomorphic to a disk. And okay, this is another important notion. If I have two objects, two topological spaces, or two manifolds that such that I can stretch one or play with the other one as if it's like Play-Doh and then turn it into the other one, they're said to be homeomorphic. So homeomorphism. Another very important thing or concept. So this is the topology analog of the isomorphism. Wherein if isomorphism dictates that two groups have practically the same structure and have a bijection between their underlying sets, a homeomorphism tells us that the topology of two topological spaces are similar and there is a bijection between their underlying sets. So homeomorphisms can go both ways. So I can turn the first space into the second space, and likewise I can turn the second space back into the first space. So two objects that I cannot, if one object, or if I have two objects such that I have to tear away a subset from the first object to turn it into the second object, we say that they're not homeomorphic because I have to take away a subset, and that breaks the rules of topology, wherein I can only stretch and squeeze it. So they're homeomorphism. And we use the same notation for a homeomorphism as we do an isomorphism, which is sim equal, or this approximately equal to. Now you can use two over here, but I use one only. Now a homeomorphism is somewhat of an equivalence relation, in which I can construct an equivalence class of manifolds or topological spaces that are homeomorphic to each other. Just like if I identify points or identify stuff or create equivalence relations between elements of a group. Okay, so let's start with the general definition of it, or how I went about it. So I have the free group over my alphabet. The free group of E compare. Okay, so I have this, so it's all possible words you can think of. Every English word you can think of, he, him, are both part of this free group over here. Okay, and I pick a symbol, two symbols that are part of it, namely phi and del. Now del is not necessarily part of the free group, but it is rather a symbol inside here. Okay, so let's say that phi be a manifold. Okay, so a manifold is our generalization of shapes. So a sphere is a manifold, a shell is a manifold, a triangle is a manifold. In fact, a triangle is just homeomorphic to a circle, including also a cube. A cube is also a manifold. Those are classifications of two manifolds, which are surfaces, basically. So a manifold is an n-dimensional manifold is a topological space that locally resembles R to the n-1 space. So if I have a three-dimensional sphere, I have a sphere, and then I zoom in on the surface, like here on Earth, you will see the Earth is a geodesic, not geodesic, but a spheroid. It is as close to a sphere as we can get. If we zoom in on the surface, it looks like two-dimensional Euclidean space, and that's why it's called a manifold. So if I take a subset U from here, and that U is homeomorphic to a subset of r to the n minus 1, then it is what we call a manifold. So here, this is a 2 manifold, n, so n is 2 here. Because in pure mathematics, it's really best if you generalize it to n. Like, you generalize it to a letter instead of just saying, oh, it's just 2 dimensions. It just works. It has to work for all n dimensions in order for it to be very significant or very useful in pure math. Okay, so this is a 2 manifold, and it is a manifold because if I take a subset here, it is, or this is a 3-dimensional. This is a 3-dimensional object because if I take a subset from this, it is, or if I zoom in, actually, if I zoom in locally speaking, globally speaking, it's all the manifold. Locally speaking, it's just a small neighborhood inside it. What I mean by neighborhood is a set of points around one point. Okay, and then I zoom in, you will notice that it looks like R2 space. It looks like 2-dimensional Euclidean space, and that is why it's manifold. Now, if a space has multiple holes in it, when we keep zooming in, I don't think it is manifold. However, you could glue the 2 spaces together, or if there is multiple holes in the space, you can glue those holes together in order for it to become a manifold. Now, torus is also manifold, and that will be a focus in today's lecture as well. Okay, so let phi be a manifold, and let this swirly d, which we call partial, be the boundary. Now, if I have a volume of a shape, like say a ball is a volume, not really a surface. The boundary of a closed ball, which includes the boundary, is a sphere. Because by definition, a ball is a set of points bounded by a sphere. Now, we don't just say or a circle. I mean, a circle is a subset of what all spheres are. It's a 1 sphere. A 2 sphere is a 3-dimensional sphere in geometry. 3 sphere is a hypersphere, or in the sphere analog of a tesseract, basically. Okay, so let del be its boundary. So, okay. So now, let's make, like the previous one, what we're going to do is identify points in the boundary over here. So we're going to construct an equivalence class. So let equivalence that takes 2 points in del and then maps it to del. Be an equivalence relation. Between 2 distinct elements in del. Okay, in del. So, for any or all a b inside the boundary, distinct, okay, the equivalence relation of A and B generates the equivalence class of A, which we denote by like the last one. So A consideration with respect to that, which is basically A and B. The equivalence class of A is just A and B. That is generated by this relation, such that they are identified into a singular point. So now, the set phi with mod this equivalence relation is the set of all possible equivalence classes of any distinct elements AB, or any element A inside del. And there is a specific topology which we equip this with in order to get to the quotient space. So I'm gonna define a family of points. Okay, so now, okay, the set is the quotient set. So the underlying set of a quotient space is this, a quotient set. All possible equivalence relations of distinct element A in del, on the boundary of this space. Okay. Now I'm making this as general as possible. Any symbol you can think of that is an English word, because I can simply just, in the end, I can just plug he, him for phi and del, and then I get my result that we want for today. Okay, so continuing on, we need to, the thing is, when we construct a topological space, we need to define what's called a basis. Okay, so it is a set of open sets such that if I collect them together into one singular set, they form the set. So let U alpha, which is a family of subsets, basically a collection of them, indexed by alpha, phi mod equivalence relation, such that for every point A in phi, I'll call X, because A is a point in the boundary, such that the equivalence class of X is in U alpha is equal to the union of, for all U inside big U of U be the basis for the quotient topology. So the quotient topology, which I will denote by tau, usually topologies are denoted by tau, tau sub phi mod, the equivalence relation, is the set. So the set of all U alpha inside phi mod equivalence relation, such that this set, all X in phi, the equivalence relation of X inside, is all inside U alpha, these families, is inside the topology of just phi. So this is the quotient topology. And to end the really boring part of this lecture, the structure, so this is the most important part, the structure phi, the quotient set between phi with respect to our equivalence relation of identifying points together. What we mean by identifying is that we make them one singular point. So if I have a line and then I have the boundary points here, when I identify these boundary points, what I mean is that I connect them together and essentially form a circle. Okay? But note that these objects are still one-dimensional objects in the light of topological dimensions and topology. Okay, going back to lecture. So the structure is equipped with that topology is the quotient space. Of phi with respect to del. And the one way we denote this is phi mod del. There it is. So box 2 and the construction. So there it is. Now, what we just do in order to actually show that, once I've written everything here, and I'm assuming you guys took note, is to say that phi is equal to he, the topological space, and del is equal to him. So I'm assuming that he is a topological space that has its own predefined topology, and then del is equal to him, which is the boundary of phi. Now, here's the part where things get arbitrary and dependent upon definition. He could be any space I can think of. He could be a literal, like, it could be a human being, right? Us human beings are just topologically the same or homeomorphic to a three torus. You know, two nostrils, one mouth, one anus, but the mouth runs through the entire digestive tract, which is simply just one gigantic tube, right? That goes in, that ends up with the anus. So we're practically just three tori, or toruses with three holes. So every guy. Now you guys can tell me otherwise, like if there's additional holes in us, like pores, you guys would think about that. But the thing is, we can bulge out those pores, you know, in order for it to become flat. So if it goes all throughout the space, if a hole goes all throughout the space, then that's when we say it's really different. So we're homeomorphic to a three torus. And so I suppose our identification space would be much different here. It would be a four-dimensional shape that we cannot quite visualize. So quotient space is very important, especially when we glue two spaces together. What we mean by gluing is we're gonna break the rules a little bit, just a little bit, and we're going to take away a subset between two topological spaces and then connect those two boundaries. So I have a sphere, and then I have another sphere. What I mean by gluing is that I take away a subset of this and take away a subset of this, and then I connect them together. So that this is actually what we call a surgery, and this actually becomes just topologically equivalent to a regular circle or a regular sphere. Because it doesn't matter, because there are no holes here. I can just shrink this into a cylinder, and then I squash that into a circle. However, things get a little funky if I say take away two subsets and then connect those together. So this is sort of the fun of topology. We get to play around with shapes and then visualize them. This shape here is not a sphere anymore, but it is in fact a torus or a donut. The torus is a surface of a donut, and it is a product between a circle and itself. So S1 cross S1 with the product topology. But that's a topic for another video. So there are many ways of defining he, him. There is one specific construction I did. However, I don't think I have the time to do this. Let's just leave it at this, that any pronoun you can think of can be a quotient space. And it's wholly how you define this and visualize it is dependent on how you define exactly what he is and what its boundary is. If we think of or interpret he as a disk, if this space over here is he, its boundary of course is him. It is the circle that's bounding all these points. Now he mod him, or he quotient him, gives a sphere. Because what we're doing is taking every point here and then connect them together into one point. So we fold it and close it up into a closed shape, which is exactly a sphere. Okay? He, him, they, them, she, her, he, they. A little extension from the last lecture is that what about multiple pronouns? Okay, what if I have multiple pronouns? Now, if you have multiple pronouns, let's say he, him, they. What we just do is simply mod out this space by that space. So we first identify the space, and then we identify it along this. If this they is a boundary of this resulting space, of course. Now, it wouldn't make sense if him is a boundary and then they is a boundary of he, because we already have one boundary. What would make sense is that if this is a new shape or new volume and they here is its boundary, then it's a new identification of that space. Okay? And likewise with groups, it wouldn't make sense if I had multiple mods here. But if it's another element that is inside that resulting modded out group, then I guess it would make sense to take that quotient. Otherwise, these two techniques of constructing quotient groups and quotient spaces from a topological space only works for a group with a normal subgroup, and it only works for a space with its boundary, topological space with its boundary. And so that is it for this lecture. So I know I skimmed a lot of very important things, especially about compactness, if the space remains Hausdorff and stuff like that, or if it is one of the T separation axioms, or it is described one of the separation axioms, if it retains those properties. I glossed over that in order to simplify the structure. So I suppose that's it. The same message from the last lecture applies here, that these are all just labels for manifolds. There's nothing new that we're doing here in terms of topology. This isn't a new concept. I doubt it is. We're just basically labeling these manifolds with a symbol instead. Yeah. So there you have it. Now, there are some constructions that are four-dimensional and we cannot visualize them. So that's that. So I guess that's a good place to stop.